semester. And again, I want to say this again to you. First, I'd like to congratulate you for attending the course for this semester. I believe that you have learned a great deal about the numerical integration of the ordinary differential equation. And for the final report, if you do the analysis of this Typhoon cross-section, you will learn a great deal. And I do not want to tell you the result now. I will let you to discover by yourself, okay? So you do the analysis, then put it into a Power PPT, then you deliver your final report, not presentation, final report next week, this time. Then after you deliver your final report, then that's it for this semester. So this one is quite good. You can do east, west, or north and south cross sections for developing typhoons, both scientifically and also very useful. So this is the real purpose of our numerical simulations. We have when we started from this semester, we talk about dynamics in the real world. When we talk about the dynamics, the meaning of the dynamics means the variable change with respect to time. Dynamic means the variable change with respect to time. So here in this equation, right, you see there's a dynamic time here. So that's a rate. Or you can say this is a frequency of change. This is the word which is very complicated, or this tornado, and we show you that we are able to reproduce the Typhoon Jangmi from the circulations and how to see how the models. So what we just show you is a real example of how we can, from the building a model to simulate the real world. What is the purpose of building the models? It's not try to just write the equation. To write the equation is good, is intellectually good. Yes, it is very beautiful. The equation, the form looks very good, but we want to make it useful. And typhoon affect lots and lots of people. So typhoon prediction is very, very important, one of the top priority. So we want to make these equations useful. So my dear student, the dynamic is not for you to, it's not for your examination. It's for your application in the real world. And you will find the value when you graduate from the university to the real world. In the future, you are not going to write the equation to make money. You will solve this one to make money. That's it. That is very simple. Okay, so so this is as we show you who did this. Yeah, and if you see this kind of process, then we want to understand what are the processes which for this chemical, for the ozone, PM10, PM2.5, how they make these predictions. And in our Earth systems, now we have experienced a quite significant climate change. So if you have a look at here, for the temperature starting from the beginning of the 19th century and also for the past 2,000 years, you see a quite significant change of the temperature recently. And how do we know the impact of this increase in the temperature, increase in the carbon dioxide, methane, and the nitrous oxides, and also the particles in the atmosphere? Are they important? Yes, of course. But how are they going to have impact to our environment? We are now, today is the 3rd of June. So if you have a look at the water, the rainfall for this May season, you will be able to see that the rainfall this year is not that significant as as we have seen compared with previous year. So we see the water we see have the water reservoir levels. Yes? Right? Oh, it's quite good. So now we have the water filtrate is for the Taipei area, Taipei, New Taipei, and Ximen area, which is in our location. So, and these are very important for our semiconductor production, especially for the Baoshan, Hsinchu, and the Baoshan second reservoir. These are very important for the semiconductor. Yeah. So now it looks very good. But for the Taichung, the Deji Shuiku is very good, 90.7. So we have a good, mostly they are still in a good condition for Taichung, Deji, 90.7. Yeah, I believe you have read the news before. During the dry season, the water reservoir level can be as low as you can see the frogs, the bronze frogs appear on the levels. Yes. And at least for the southern part of Taiwan, but this reservoir are smaller, or we see the water level is very low, right? They are all red. Oh, Zhengwen, Jesus, 9.4. Good gracious. Almost dry to the bottom. Ouch. Yes. So here you see clearly, right? For the water reservoir over southern Taiwan is very low, but for the water reservoir, central to the north Taiwan is very high. So why? You must be able to explain this from the meteorology, right? So what I want to say is these are the very important demonstration for Thailand Zhengwen. Oh, Jesus, Zhengwen is so low. 9.4 is almost to the bottom. And the Kaohsiung Agongdian, oh, Jesus. I met a friend yesterday, and he told me that he lived in Henchun, and there are about 3 months without rainfall, like in the desert, like in the desert. So what I have shown you is that climate change has a big impact. Our country, Taiwan, is very small, right? But you can see that from the north to the south is about 450 kilometers, but the climate is completely different. Isn't that beautiful? Amazing, isn't it? So congratulations, you are in the Earth Science College. And that is very. So again, this kind of big change, which is going to have an impact to our civilization before. Now it's here. So we are now in we call interglacial period. And this is the glacial period, interglacial period, glacial period. For the past 220,000 years, we see this kind of cold, warm, and cold. Isn't this looks very familiar to you? Very much like a butterfly effect, right? You have phase diagram, phase change. From here to here, from here to here. So that means we are very lucky because we are now in the interglacial periods. And but from this data, you can see in a longer period of time, the Earth, the climate is in the cold periods. So the carbon dioxide, the greenhouse gases, they play a very important role. So if we go back further for the past 650,000 years, we can see this kind of the warm, cold, warm, cold, warm, cold, this kind of change. Very much like the Lorentz models the change of the phase between this one and this one. And yeah, it is quite significant. And we can always find that the change in temperature are associated with the increase with the greenhouse gases. The change of the long-wave radiation budget in the atmosphere change the energy budget. So from the isotope in cap, in the bubble, in the ice tube in Antarctica and also over the Greenland, we can find the isotope ratios and to determine their past climates. Because the warm period and the cold period, they will favor various kind of the isotopic concentration. Okay, so this is very significant. And you know, you see this, right? You know. So for this butterfly effect, you are now can do this very well by yourself. So we see that ice age as a history, not necessary. Anthropogenic climate change will basically produce another planet. Yes, it's going to be warmer. Earth won't have another ice age until until human go extinct. James Hansen, he was very angry. So he said this. James Hansen, yeah. But this is a very strong word. Okay. And the reason for that is because we have if you come back to here, why he said this, that, you see this looks very unnatural, right? A very long period of time, and it goes up very quickly within 200 years. So why it goes up? Why? Because of the Industrial Revolution. Now, why the Industrial Revolution has anything to do with the increase of this concentration? Because of the burning of the fossil fuels, right? So you have increase of the carbon dioxide and also the methane, natural gas, the coal, the oil, and also the use of the agriculture to grow food for the population. And also the sulfur as well, because of the activity in burning and also all of the construction process. So my dear student, this is a big change, and you will see this, and I will see this as well myself. And but now, luckily, we are now in a better situation to face this one. Why? Because you learn how to run the models, to understand the process, to build the things which can help us. And when you build things, now we are in a much better condition. Why? Because of this. When I was at your age, when I was at university, when I was at the National Taiwan University, we did not have this kind of things to help us. But now the things has completely changed. So you see here, I just use this. So I say, you can ask everything. So are we? Right? Then you will find the data. No, we are not in a good shape. You see that? I asked him, are we we are not in a good shape to prevent the worst impact of the climate change. So, my dear student, when there is no water, which means no water. When the water reservoir is dry, then which means dry. No water means no water. Hey, hello, listen to me. No water means no agriculture, no food. We human, we cannot eat dirt. We cannot eat grass. And no water, no grass. all the dirt is going to become dust. Dust is going to be alien, go to the air. So yes, no, I asked, are we in a good shape in combating climate change? No, we are not in a good shape. Yes, very honest answer. So AI is not going to lie to us. To prevent the worst impact of climate change, though we are making unprecedented technological process. Yes, 10 years after the signing of the UN FCCC Paris Agreement, the world is caught in a profound contradiction. We are building green infrastructure faster than ever, yet our total emission and global temperature continue to rise to record height. People still want to use cheap energy. They want to, and the burning of the fossil fuel is quicker than to get the energy from the renewable energy here, right? These are the free energy here. We just let it go. It comes, it goes, and we complain about hot weather, and we are unable to convert. This is energy. These are our energy. You see, if we touch the window, it's warm. These are our energy, right? During the cold winter, you like have this kind of cold temperature. You have to have this. These are our energy, but we just let it go. If you imagine every grass, every leaf outside is a solar cell, can you imagine how much energy, how much electricity can be generated? So there are lots of things to do. So my dear student, I would like to encourage you to do something about this, and this is your opportunity. Okay, you are not at the end. Do not never say that everything can be done has been done. That is not true. We are far away from our human potential. We only burn the fossil fuel for 200 years, and here you see only 200 years, and then we end up with something like this one. We call this one as hockey curve. Hockey is like a rod that you use to play golf, right? You have this kind of a shape. Or you play ice hockey game. So we call it hockey curve. Right, and yeah, we have this kind of emission. We discussed this in the environmental chemistry, and we don't say this one. Okay, so this is our beautiful country. What I want to show you is something like this one. So when we do the model calculations, we call this one as a grid, or we call it a resolutions. So we solve the primitive equations at each grid point. Then we combine them together. So when you see the typhoon here, that is because we solve the equation, and the communication between this one and this one is due to the horizontal flux from here to here between, and also from the lower to the upper boundary. This is our model prediction. When we do the numerical weather predictions, we need to solve the system on the grid. And in this semester, you already know how to do the integration of the weather, of the differential equation, but on a single point, or we can say in a box. We call this one box models. But every complicated model is built from the model like this one. So we can check out the calculation here. So later I will show you a simulations which we did by ourselves, and we compare our result, which is in the color, with the satellite image. So let's see this one. Yeah. So this is how we do the simulation. You see here, we simulated the transport of the dust across the North Pacific, and we trace millions of the particles. You see again? So this is from the Gobi, and it has been transported across the North Pacific. Here you can see the westerly frontal systems, and goes back toward across the North Pacific is from the below 3 kilometers, 3 to 6, and about higher than 6 kilometers. So by doing this kind of simulations, everything you see here was done by Fortune, no Python. Why no Python? Because at the time when I produced this product, there are no Python available. We have to use Fortune. So Fortune is forever. It's very good. Right, we can also compare with the satellite imaging. So in this case, the yellow means the yellow sand, which are lifted into the upper troposphere by the wind, then compare with the satellite imaging, which is the background gray colors. So let's see again. So this one is the Takanamakan, and this is the Gobi, and the dust has been uplift due to the frontal disturbance. You see here, you see the shape, right? This is the westerly frontal shape, then being suspended in the upper troposphere. And if you compare with the satellite imaging, then we are able to understand the impact of this transfer. And we also can also compare with the infrared satellite cloud top temperature to see the importance of this kind of the dust transport process. So you can see clearly that they are associated with the climate systems. So here are when we do the weather predictions, it is very important for us to verify our results and compare with the real situation. So these are from our simulations. This from the true color from seaweed satellite true color image. So from this case, you can see the yellow dust. The yellow dust has been swirled into the mid-latitude cyclone systems. You can see here, which is also the process we are able to reproduce from here. Then from this one, we can simulate we can estimate the process which will be impact to, for example, to Taiwan from the Gobi and also from the Takanamakan area. So this kind of the process is very important to help us to do the calculations. And then you see here, so let's look at here. This one is amazing. So when the air comes down from the north, because here is colder, so you see here, it will confine to the lower, to within 1 kilometer here. So when the air comes from the north to the south, and it will confine to very low altitude. So if you go to the mountain area, you will see a different air character. You see what? And you can see the frontal structure, right? Frontal structure, very much like the one you see from the satellite image. And this one is from the Takanamakan desert. Again, we trace millions of the articles of the particles, and then we can compute their effect. So if you, this is the reason we very much like the following report we suggest you to do. You can do a more detailed analysis to understand the process which you have learned during your courses, your various courses. In this case, we learned the long-range transport. What do we mean when we say long-range transport? We mean the particle being transported hundreds to thousands of kilometers, which can be maintained in a very good structure, which is here, and to approach Taiwan. This is we call the transboundary transport. So in this case, you see when a pollutant touch northern tip of Taiwan, touch Kilo, it is about 1600 local solar time, and about this is 12 hours later. 12 hours later, the pollutants will go to pass the Hengchun. So you see here, the front. The front is very much like the satellite, the frontal structure you see in a satellite cloud, right? It's very much like the same. So this is the wind you have learned from your courses. Very beautiful. So approaching Taiwan, and it confines to very low. Then 12 hours later, it goes to here, to the Hengchun. So what does that mean? If in 1 day there's something, we hope it will never happen. We will have a nuclear power plant, still have 2 nuclear power plants here. If something happens, then if you want to prevent yourself from the nuclear reactive materials, what you can do? Go to the mountain area, because the particles were confined to less than 1 kilometer. Goes up, go to the mountain area, go to Lalasan. It will be good for you to keep yourself away from the incoming pollutants. And this is how we see this kind of the effect very significantly. We verify our model calculation with the observation. Only by doing this, we can convince ourselves we are doing the right thing. And when you do the right things, you are able to make a prediction. Okay, so this is the essential things, and for the climate, for the NWP models, which I love very much, and I have spent lots of time doing this. And of course, you can still do some with this capability. You can run simulations. For example, this is the Antarctica ozone hole. You can see that the air inside the Antarctica region has been confined for more than 100 days. This is the reason the ozone hole can develop here. The temperature is so cold so that the chemistry can have a process, can occur on the ice particles. So, and then these are all important for us to understand these climate systems. So if you are interested in doing an advanced study, master or PhD study, and if you say, I do not have money to do that, don't worry. For this kind of research, most of the research institutes, they will offer you the free or the full scholarship to do this kind of studies. For example, for this, we call this as a global biogeochemical cycles. And you including the effect of the ocean, oceanic phytoplankton, the biosphere in the oceans, and the biosphere over the land, and the chemistry, the physics, the incoming short wave, outgoing long wave, and a very complicated process. There are lots and lots of funding for doing this kind of research. So I will encourage you, if you are interested, to do this kind of the studies. And this is the model we built. This is the model I built by myself to do this kind of calculations, all with the fortune. Okay. So finally, I'd like to show you something. There are lots and lots of good things to do. And let me I think I have maybe I've shown you this before. This is the final simulation I'd like to show you. And this is an exercise that let's see here. Okay, these are the final stuff I want to show you. What I want to show you are the exercises for the students in this department 10 years ago. Now 10 to 15 years ago, they have to solve this equation. This is a 20 by 20 maze to write a code. If I got an entrance from here, then I want to go. Have I shown you this? Have I shown you this? Okay, so let's look at this. This is a maze. So you want to go out from here, right? Then you want to get out from here. This is a 20 by 20. So this is an exercise for your very senior sisters and brothers. So we can write a code, a fortune code to write this. So we use computer, no Python here. At that time, 10 years ago, no, we don't use Python, just use logic and process. So you will find a way, you see? Yeah, then you find a way to go out. So this is the exercise before, so we can, right, you can find a way to go out. And all the red circles here are the exploration. So this is a 20 by 20 matrix. How about 100 by 100? How do we solve this one? Yeah. If this is a 100 by 100 matrix, if entrance here, axis here, this is homework for students before. Then again, similarly, we can write a computer code to do this. It's a computer they are very nice. So in entrance, we are here, right? So for each breaking point, we separate. So the logic is very similar. And we use this simple reasoning process to find the result. And we use the iterative process to solve this one. So at that time, every student has to write this code to solve this one. And they did it. Yes, they did it. Of course, they have to suffer a lot, to struggle. but I did it myself. And I wrote this code myself as well. I did not write this code by asking ChatGPT. No ChatGPT 10 years ago. No. But we have the Fortran code, you have the logic. So you know the logic and you know the principle. You can write the code to solve this one. And so it's quite beautiful to see. These are all the evolution process. And the reason we do this is very similar to the one when you integrate your ordinary differential equations. So at each time step, we produce a friend, then we combine all the friends together. You can get this kind of the result. So here, you can see clearly that naturally, the nature will find a way toward this direction. Isn't that amazing, right? The logic is very simple to find your way out. The principle is to find a way out. And for every location, you spread out. And if there are no way to go out, then you die. So you see here, so these are all going to die, but these are going to survive. But no one knows which direction is correct, so we don't know. We just keep trying. So in a sense, this is very much like artificial intelligence. We put lots and lots of data to the computers, and it can help us. It can help to find the pattern. And the pattern is in the parameters, the weighting function, in the weighting here. So you see here, all of this part, they die, but only this part, they survive. And so when you complete the code, then you will suddenly realize it is very powerful. Yeah. Yes. So you find the way out. So this is out. It enters from here, and it goes out from here. So we can use this one as a secret code. This is a password. You have to match this password. And it has searched all the red space has been searched. Only the blue, this to the exit. So, yes, so this is the final plot, and I hope you enjoy it. And I hope you enjoy the course for this semester. And finally, I invite you to spend time for your final report, okay? Then next week you can come here and then to deliver to just give me your report, then you can go. Then that is for this semester. Thank you. I see you. Good luck to you. Yes, okay, wait a minute.